Multivariable Calculus 15.9, our third video, just finishing up this very last problem. We're just trying to write a triple integral that would represent the volume of this solid. And guys, as soon as you know that you're working with spheres and you're working with cones, chances are spherical coordinates can be very, very helpful. Here's a very important link. You might remember that volume integrating over a solid can be found when you just put 1 inside your integrand. So of course we're going to jump over and convert this volume, this integral I should say, into spherical coordinates. But that's going to beg the question then, what are the bounds for these three integrals? So as we're looking here, maybe we should look really at the top with that sphere. And the original equation, x squared plus y squared plus z squared equals z. Let me just do a little bit of work off to the side here. And remember, x squared plus y squared plus z squared, that's rho squared, isn't it? And z was rho times the cosine of phi. Now, if I were to divide both sides by rho, we'd have rho is equal to the cosine of phi. So what we're really getting at, please understand this. This sphere right here could be written as, wonderfully, that rho, pardon me, is equal to the cosine of phi. So, of course, this solid, imagine that we've got the cone and the ice cream, our R value, our distance, is going to span anywhere from the origin. It can go as far as this sphere right here. So what are we going to see? The boundaries for rho, we're going to go between 0 and the cosine of phi. Now, when we're looking at the cone, as we're looking at this cone right here, I think that also begs the question. You can think, what in the world is going on over, you worked with that top portion, what about down below? Well, remember that z, we just saw this a moment ago, was rho cosine of phi. But my goodness, we had x. And let's just review a little bit. X was going to be rho sine of phi cosine of theta. So that's your x squared. And then our y was rho sine of phi sine of theta. So just looking at this other portion of our graph, is we're looking right here, we might think, well, can we maybe get some help in this regard? Well, look, inside we're going to have rho squared sine of phi squared, cosine of theta squared. Here we're going to have another rho squared sine of phi squared, and here we'll have a sine of theta squared. And I hope what you're noticing right here is that those two items, the rho squared and the sine of phi squared, show up in both. So tell you what, I'm just going to factor that out, leaving us with the cosine of theta squared plus sine of theta squared, which, by the way, most famous trig identity of all, that's just a 1. And then very quickly, this square root would just be rho sine of phi. So, hey, look at this. It doesn't take too much to see we can divide out our rows. And you're really saying what angle cosine of phi would equal the sine of phi. And you can say phi would have to equal pi over 4. Just wanted to call to your attention the beginning of our notes when we were looking at a cone. You might remember that we said that phi could equal a constant to get such a shape. So that's very, very important. We now know that our phi can get as big as pi over 4 and as small as 0. That's actually the last constraint for phi there. And then what about theta? Well, theta, you can see as you span around, you're going to go a full 2 pi radians. So this right here really is the triple integral that is going to allow you to find this volume. And that wraps up lesson 15.9.